Okay, let us talk about curvilinear dynamics. Curvilinear dynamics. So far, we talked about rectilinear dynamics, which was very convenient because we used a single um, frame of reference, which was static at a point O. And the concept there is that this was an inertial frame of reference. So it could also be moving or static, meaning that the Earth is moving, but it's an inertial frame of reference. So concept number one that we have to realize: inertial frame of reference. And the inertial frame of reference is very important because that's the basic assumption for the laws of Newton to work. For when we say F equals ma, remember that we're doing the kinematic analysis, and the kinematic is the characterization of the geometry of the movement. So when we say that, this is based on a inertial frame of reference. Remember, the force and accelerations are vectors. Those are represented with respect to an inertial frame of reference. And the way to remember or to decipher if an inertial frame of reference exists or not is picture a train, and there's a table on the train, and there's a tennis ball or a soccer ball. If the train is moving at a constant speed, could be speed of light or less, but it's constant, the ball is going to be in an inertial frame of reference. So basically, what we can say is that if we put a coordinate system or coordinate system at the ball, okay, that's being our center O. This coordinate system could be used to measure anything else on the universe because it's an inertial coordinate system. But on the other hand, if we have a dynamic system, say again we have a train cart, and the train cart is accelerating, meaning that the velocity is not constant, then when we place the sphere on the cart, this ball is going to have a velocity or even an acceleration. Okay, it could go depending on we know by now that depending on the shape and form of the acceleration curve, this could have a velocity, negative or positive, but this is not an inertial frame of reference because now our coordinate system has its own energy associated with it. Okay, so in this case, which we have an inertial frame of reference, the minimum energy concepts apply. And that's, you might learn about those later in other topics, but we need an inertial frame of reference, meaning that our ball is not accelerating, it's not an accelerating frame of reference. Okay, all right, so when we have an accelerating frame of reference, that cannot be an inertial frame. So before, everything that we learned was from inertial frame of references, right? We had a function, we computed velocities, accelerations, etc. Well, now that we're going to talk about rectilinear functions and curvilinear functions, and now that we're going to talk about rotating frames of references. then it's very important to realize that they have to be based on an absolute frame with origin O. So let's go ahead and decipher how to represent a rotating frame of reference. So let's say we're going to start from our coordinate system X and Y, where this is our origin, and we're going to have, say, two planets. So they have a big enough mass. We have planet A and we have planet B. Right? And say, or we have planet B and we have satellite A or whatever. Say the point is that in this example, let's assume that we know the conditions of point A. We know the velocity and the direction and everything from point A because it's the satellite. And from there, we want to decipher the direction and velocity of point B. Okay. So in this case, if you remember, this could be expressed as R from A to O, right? Head minus tail. And this is R from B to A. And this distance is R from B to O. Okay, so far so good. All right, so now that we have that, we want to characterize the movement and acceleration and distances from point A with respect to O or respect to A. So again, before, let's compare to what we know. Before, with the rectilinear coordinate system, with the rectilinear approach, this x-axis and y-axis were fixed, and we said that that's I component and j component, and if we had a vector, so we had an acceleration vector with components in the I and j direction, you can derive that or integrate that. Say, let's make this easier. Let's say this is not velocity, this is not acceleration, but this is velocity. When you differentiate velocity with respect to time, then you can differentiate the function itself, but the components remain constant because they're the unit vector. Well, here it's not as easy. Here these distances can change. So basically, if you want to change, if you want to compute say we want to compute the velocity of the point B, so we would say the change in distance of B with respect to O in time, this distance with changing, so if you change the distance in time, you're gonna get a velocity, right? So we can find the velocity is equal to the change of the distance of A with respect to O, which will say it's the satellite that we know that velocity. We're trying to compute the velocity of a planet B. This is how it's done actually, based on different things that we already know. So we know the velocity of the moon, or we know the velocity of the satellites. So we use that and we differentiate that distance plus the distance of B to A in respect to time. Okay, so let me clean that up a little. So this is B, this is velocity. In case you want to see the notes later on, you remember. All right. Okay, so far so good, right? We have the change in direction, the change in distance of the vector r with respect from B to O is the same as computing the change of distance of A to O plus the change of distance from B to A. All right, we can do that. All right, so now let's introduce the rotating frame concept. So let's assume that we have an orbit that is completely spherical or circular. Okay, and then we have our point B right here. And at the center, we're going to have our point A. Let's say that's the center. Okay, so evidently, this distance right here, that's going to be the distance from B to A. Right, so if you picture that, we have an orbit right here. Okay, B to A. And then allow me to characterize these even further. We're going to say, let's use, what color can we use? There's different. Is green, are we able to see green? Let's see. All right, and we're going to have an x prime and a y prime. So, you know, when this is rotating, so when B is right here, then x is going to be the radius and y is going to be perpendicular. All right, so the x prime, let's put it over here. X prime has component I prime, and y prime has component j prime. Okay, so we're going to use a secondary reference point that is Cartesian. Okay, and A is at O prime, but let's just call it A. And let's assume that this orbit is moving the velocity A, right? We can do that better. So velocity A. So basically what we're saying is that it's a particle, a satellite moving with a velocity A, and there's another particle rotating in a rotating frame, and that's B. So not only this particle is moving with a velocity A, we also want to compute the velocity and displacement of the particle B with respect to A, and also with respect to O. So say this is O. X, Y, okay, and then when it moves there, you can also move here. All right, so this distance can change. Therefore, the change in distance with respect to time needs to be computed. So this distance can be all that, but always remember this particle A is moving with a velocity, and that velocity could be rectilinear, or it could be also a path. So it's getting complicated, as you can see. But the basic point is to start from here. This is the basic point to start from. The change in the direction of B with respect to O is equal to the change in direction, the change in distance with A from O, this right here, which is changing in direction with time, plus this distance right here at every instant. All right, so let's do that. And the way to do this is basically by applying our concepts of dynamics. So let's go ahead and start trying to decipher what we need to do. So this concept right here is a velocity. So velocity of B with respect to O is equal to the velocity, and notice, first of all, that this right here, this is the position or the velocity of B in the rotating frame. All right. All right. Now, the velocity of A with respect to O, this is the frame velocity, right? Because now our frame, let's go back to green, our frame is the radius formed by that distance B. And this is orthogonal, perpendicular. Okay, so this is the rotating frame right here. X prime, Y prime is rotating frame. Right. So we have velocity of A with respect to O is equal to the velocity of A with respect to O plus the velocity of B with respect to A. But let's focus on this part for a minute. If you notice, the velocity of B with respect to A is equal to, well, we need to know what is the rotating velocity though, which usually is called omega or W. Omega Greek letter. Okay, so the velocity of A with respect to velocity of B with respect to A, this particle B with respect to A, is equal to the angular velocity with respect to O. So this rotating velocity with respect to a fixed point somewhere else in the universe, could be the sun, plus, oh sorry, not plus, but this is, remember from statics, this is cross product, cross the distance of B with respect to A. Remember this curl, this cross product. So is the angular velocity of the frame cross the distance of B to A. And this is very good because if this is not a sphere, a circle, but an ellipse, then you can take care of the path just by characterizing this distance. This is the kinematic portion. This is deciphering the geometrical changes of your velocity, of your accelerations. So if it's a sphere, it's just a regular rate, it's a fixed radius. If it's a circle, it's a fixed radius. But if it's an ellipse, then you have an r that is varying along your path. Okay, so in that case, we're good because what we need to do is say, okay, so I have my velocity of A with respect to O. Now we have to put my velocity of B with respect to A. But the interesting part is that this has two components. This is only with respect to X prime, Y prime, Z prime. Z prime is perpendicular to X and Y, right? It's pointing out from the screen. It's basically pointing at us. Okay, so this is the velocity if you look at from O, right? Sorry, this is the velocity if you look from the rotating frame of reference, but we need to do it from O, so from the origin. So in that case, what we need to do is add the velocity of B with respect to A, evaluated at your inertial fixed coordinate point at O. Remember, this is O. And now you can introduce the term of the rotating frame. Cross product R B So the velocity of the particle B, which is rotating in a certain path, is computed with the velocity of the frame itself, because remember this point A is the origin of our um, reference relative frame, x prime, y prime, and that is right here, plus the velocity of the particle B with respect to the absolute frame, plus its rotation at a velocity omega. And obviously, in order to know what the velocity omega is, we have to know what is the radius. So omega cross the radius of B to A. As we mentioned, if this is a circle, then this radius is fixed, this is a constant. If it's not a circle, then we need to introduce a function right here